let temperature be 20 if you are optimistic, 30 if you are realistic, 40 if you are pessimistic. Specify your temperature and then pick the density from the table or tables given. Now, if there is some data not given in the table, then it is my responsibility to include in the table. For example, if the size of the gate, it won't be there in the table. So, syllabus is everything covered up to Wednesday, and Thursday is your quiz. And then the second quiz probably will be first week of September. Okay, and then you are ready for the mid-semester exam. Quiz will be of 20 minutes duration. At the end of the class. So, we are in the process of deriving the equations of motion. So, we have looked at the global version defined for a control volume. So, this is how we have defined our control volume. It is a space containing the fluid medium. Suppose there is an object inside, then the control volume will exclude the object. So, you will have control surface 1, control surface 2 covering the object, and the space in between is control volume. The analysis is carried out for the fluid medium, continuously distributed fluid medium. But in applications, we are always asking this question: what is the force acting on the object? The solid surface is the key. The analysis is of the flow field. So, that is how you know from your reading of newspapers. So, if you have a tall building and there is flow, it experiences forces, but you have to analyze the flow field to get the forces. You have devices like, let us say, turbines, where it is the flow field that drives the shaft of the turbine. If you think of an aircraft, of course, there you do not have a flow, you have an object moving relative to the fluid, which we think of as flow past a stationary object that generates forces. Now, from the global version turned out to be an integral form, hard to solve, but easy to approximate. We just write the integral as average value of the integrand multiplied by the volume if it is a volume integral, or surface area if it is a surface integral. But when you approximate or estimate, you get of course the approximate solution. So, quite a bit of details are lost in the process of approximation. So, if you say I want the exact solution, then it is preferable. You can't solve the integral equation because our state of knowledge has not reached that point, but we try to convert integral equations into a differential form and solve differential equations. So, that is then called a local approach. The local approach will give you the local solution. So, that is velocity at any point, which also means velocity at every point. So, that was the approach we used in hydrostatics, where we got pressure distribution, and then we integrated pressure to find forces. So, you could do this. So, local can take you to global, but global gives you global information and that is it. You can't go back to local. I mean, we have been giving examples. Is the class doing well? Maybe yes. But is this student in particular doing well? We don't know. That is local. But if I know the performance of every student, I know the performance of the class. It's an important perspective, because in chapters 3, I think probably 4 also, it is a global perspective that we adopt, and then later on proceed to a local approach. So, in the later part of the course, we will talk about finding the velocity distribution, and from that distribution find stresses, from stresses find forces. That approach comes a little later. So, global is what we start with and spend some time. So, in the local form, we go from CV to the scale of a control volume to the scale of a differential element, and hence a differential equation. So, you can solve for u, p and get stresses to forces, and forces moments are considered equivalent. Okay, so, what we call a momentum equation is a linear momentum equation. The book keeps talking about a linear momentum equation. Sometimes it is useful to work with an angular momentum equation, but there is no new information in it. Just taking moments of the forces. But force and mass, for example, or energy, these are all very distinct. So, in terms of attributes related to the natural laws, we have mass, momentum and energy. You may think of entropy, but that is more like a constraint. And for momentum, it is mostly linear momentum or angular, not and angular. So, rather than rewrite the Reynolds transport equation, let me write the mass balance equation straight away. So, in integral form, the global form of mass balance equation just restates the conservation of mass principle. And then very often we use, let us say, a steady state version in which the first term, the time derivative, is 0, and even more common is incompressible, where density is constant. Reduces the governing equation to u dot n ds over the surface area of the control volume equal to 0. So, these integrals are evaluated as estimated, approximated. You do not have to, there are some, these methods are slowly being developed on how to solve an integral equation. So, you can solve it, but for the purpose of our discussion, we will evaluate the integral as average value of the integrand multiplied by surface area. This is the global form. The local form was obtained this is the local form of the mass balance equation, which is applicable at a point and at a time instant. So, that way it is local in space and time. Rho is in this version is a function of position and time, velocity is a function of position and time. Okay. If you have an ideal gas, let us say, then you can express rho in terms of pressure and temperature. Okay. So, if it is a compressible liquid, then rho becomes a function of pressure, only pressure. Okay. So, those equations, what are they called? From thermodynamics, you know, those are called equations of state. Okay. They encapsulate the microstructure of the material, whose behavior at the macro scale is represented by the equation of state. So, this is the local, and if incompressible, so the term used so if the question is the flow field incompressible, check del dot u. If it is 0, it is incompressible. Or alternatively, if it is given it is incompressible, del dot u is 0. Then we proceeded to the momentum equation. Where this is F, which is the sum of all external forces acting on the control volume, which means on the fluid contained in the control volume, is equal to integral over Cv So, this you will notice is now a vector equation, because force is a vector. This is the first term, and plus integral over C s rho u u dot n ds The incompressible steady version will not have the first term on the right hand side, time derivative being 0, and the incompressible form where rho is constant is given by f equal to integral rho times integral over Cs ds. So, now you can have two approaches. If you know f, you can try solving for u, but in the initial part we will estimate f by approximating u. Okay. So, when we approximate u, then you can evaluate the integral as average value of the integrand times area. That will then estimate the force. So, you have to remember it is an approximation. Like I said, in engineering, always we just do not have time to get the exact value. I think you will appreciate it if I say we need jobs for students now. If the person says, let me understand the intricacy of how a pump works, it may take me 8 years. Suppose he says that and he delays setting up the pump factory, then that much of employment is gone. You want employment now. So, you use your own gut feeling, use tools like this to approximate, estimate, and say, this pump should work, make that pump, try it out, and then do some improvements along the way. So, the whole process is now accelerated, compressed, condensed, and you set up the factory in 1 or 2, maybe 1 year or less than 1 year, rather than 8 years. So, the power of approximation and estimation has real impact on all of us. It's in that spirit, though of course, the problems we look at and the problems given in the book are enormously simplified, so that the point is made rather than going into the device specific details. Two types of details: details relevant to fluid flow, that we will not diminish to the extent possible, but device specific details, what is a nozzle, what is a turbine, what is an aircraft, those details you will learn in other subjects, but mostly device specific details you learn on your own. That is the way the courses are set up. Okay, so we also had an alternate form that prescribed the force entirely in terms of the volume integral, because it gave us the familiar interpretation that rho dV is mass. So, F is equal to mass times acceleration. So, you will see that it is very, very generic, because CV is not specified as a cube or a tube or any specific geometry. But why is this term acceleration? So, this you may not have, maybe in your rigid body analysis it's not emphasized, but this acceleration is always attached to the mass being analyzed. So, in our flow field also, let us say this is the flow path and the particle moves from A to B. There is a particle and the acceleration of a fluid particle, that is what is defined in the conventional mechanics framework. So, we write acceleration. So, you can think of it as scalar acceleration or vector acceleration. As this derivative changes in velocity as you go with the particle from A to B, which is u b minus u a divided by delta t, the time elapsed in the limit delta t going to 0, but the derivative is evaluated as the particle moves from one location to another. This is our understanding of acceleration. Then how come the integral partial derivative of u with t plus u dot del u, why is it acceleration? So, that is easily established through a mathematical identity. If you write u to be a function of x and t, then the total derivative is equal to and there will be a third term also if it is in 3 dimensions. Now, this derivative, these x and y are coordinates of the point being studied or the particle being studied. So, these are u and v. So, here let me introduce the notation. This is x coordinate, y coordinate. The velocity component along x is given a symbol u, and the velocity component along the y direction is given a symbol v. Now, books tend to be as general as possible. So, they will also have a z direction. For the z direction they use w. So, u, v, w are the Cartesian components of the velocity vector. So, this you can see is just this derivative. See, u del u will have components u x, u y. So, which is just this form, this acceleration form. So, often I think in this book also this suffix is used to indicate partial differentiation. Okay. So, you understand the difference between total derivative and partial derivative. So, these are all partial derivatives defined with respect to a fixed frame of reference. So, we have this important result where this del u will have components u x and u y. And u dot del u will be u x plus VUy. Now, why this roundabout way of defining acceleration? Now, this also is subject specific. I think 2 lectures ago we talked about how we are now forced to work with control volumes rather than control mass kind of an approach. Here we now see that it's the equations take you to a sort of a very elaborate form of acceleration. You will agree with me that du dt, that total derivative on the left hand side, looks simple and elegant, but it has to be evaluated along the flow direction. But that flow direction is not known to you to start with, that is what you want to find out. So, the left hand side is not in a form that can be evaluated. How about the right hand side? The right hand side, yes, because your frame of reference is fixed. What is the meaning of del u del x, partial derivative of u with x? That means you put the frame of reference there, and it's just u at the neighborhood point minus u at the original point divided by delta x, and there is no reference to the flow direction. There is only reference to a coordinate system which is with you. It's your free will, so to say. So, the right hand side, similarly derivative, partial derivative of u with time is at the same point later minus now divided by delta t. Okay, so, it is along the time axis. So, the right hand side is easier to evaluate and is a preferred approach to solving fluid flow problems. So, there are names attached to these derivatives. So, this form, the left hand side, is often called the Lagrangian form of acceleration, and the right hand side is called the Eulerian form. So, needless to say, Eulerian is preferred over Lagrangian. Now, no statement can be absolutely unconditional. So, there are some books, some authors, some thinkers who prefer to work with the Lagrangian form, but I can safely say as of today more than 95% of engineers dealing in fluid mechanics prefer the Eulerian form of acceleration. So, you can think of Eulerian as traditional and Lagrangian as non-traditional. Okay, so maybe I can dwell on this subject of acceleration a little more. In the Eulerian form, this derivative is often called the temporal derivative, so or temporal acceleration, and the second term is called the spatial acceleration. Okay, so, you can think of a fluid particle, if you just stay at the same place and find out if velocity changed, as in unsteady flow, then if velocity did change, then you would say the particle has temporal acceleration. Then in spatial acceleration, you move from one point to another, and if the velocity field over there is different, the particle will adopt that velocity field. Therefore, there is a change in velocity due to particle movement. It's spatial. You see the acceleration part of it because the particle has moved from one point to another. And the sum of the two you can think of as total acceleration. So, last time we were talking about this example of flow in a tube. Okay, so, the first step is like in solid mechanics, you set up the control volume, which is equivalent to the free body diagram. So, and then label the corners A, B, C, D. So, this is a control volume enclosing the fluid space. Flow is from left to right. These are surfaces 1, 2 and 3 is the solid wall. We do not have to do it, CV can be anything, but we make the side boundary 3 overlap the wall on the inner side. Then you can apply u dot n equal to 0 on that surface. Then we got two important results. First was u1 equal to u2, and the second was we got this result f x component is equal to we had that was the evaluation of this integral. So, we wanted the x component. So, you replace u vector by just u. Okay. So, and u dot n is evaluated respectively on various surfaces. So, this turned out to be rho minus u1 square a1 plus u2 square a2, and a1 is equal to a2 and u1 is also equal to u2. So, this turned out to be 0. Okay. So, the sum of all external forces acting on this control volume is 0. So, just to give you a counter example, and what is it useful to say sum of all external forces equal to 0? So, we will see some utility in getting that answer. So, we solved the mass balance equation and we got one result u1 equal to u2. What is u1? It is the average velocity in the axial direction on the inflow plane equal to average velocity in the axial direction on the outflow plane. Two are equal. If they were not to be equal, there would be accumulation of mass inside, resulting in unsteady effects. There would be continuous change in density. Okay. But since we stipulated steady flow, u1 became u2 and then equal to u2. So, suppose the flow is steady, but compressible, then you would have rho 1 u1 equal to rho 2 u2, but rho is of course constant in the analysis of last time. It is like flow of water, that is what I told you. I keep telling you it's like flow of water in the hostel. So, in the hostel many tubes, many sections of the tubes are vertical. So, we will look into vertical tubes as we go along. And ultimately the question is what should be the pumping effort? Do I need 1 kilowatt or 1 watt, 1 milliwatt, etc., or 1 megawatt? I hope you have a feel for it. 1 megawatt, is it a large power requirement or a small power requirement? You tell me. 1 megawatt is very expensive. Huh? I think this campus consumes maybe what, 6 or 7 megawatts. That's the peak power consumption of this campus. Which is a large amount, of which almost I was told 25% of it, a big chunk of it is air conditioning. Okay, so a geometry like this, where the area increases in the flow direction, is called a diffuser. So, it's just talking about a tube, but a tube with expanding area. So, here A1 is not equal to A2. So, the analysis will give you U1 A1 equal to U2 A2. So, let me say incompressible again. This is the mass balance equation. So, this is the CV. A, how did I so U dot n is again 0. Now, something has to be said about this U dot n. What is U dot n? It is the normal velocity component on the solid surface. Now, this solid surface is a boundary of the fluid domain. So, fluids, we keep talking about fluids, but they all have a boundary. So, there is a confinement effect. Now, if flow does not pierce through the solid surface and come out, then U dot n, the normal velocity component, is 0. So, that is sometimes called a boundary condition. Okay. So, but if the material is, let us say, like a mesh, suppose the tube is permeable. Okay. So, it is you make a tube out of a mesh. Okay, and there is flow taking place inside the mesh, then flow can come out through the mesh. So, U dot n is not 0. So, we are talking about an impermeable solid tube, solid in the sense there are no pores in it. Okay. So, impermeable, so, then U dot n normal velocity is 0, that is a boundary condition. The other type of boundary condition that we will be referring to is the relative velocity between the fluid and the solid surface. If you remember Newton's parallel plate experiment, the top surface was given some velocity, and sort of immediately we said the fluid also has that velocity. That means that fluid was sticking to the solid surface. The relative velocity between the fluid and the solid was taken to be 0. So, sometimes called the no slip condition. So, in the tangential direction, we often use a no slip condition. Okay. That is, the fluid sticks to the solid surface. If the solid surface is stationary, fluid is also stationary at the wall, but it is moving inside, which means a velocity has a distribution inside the tube. We are solving not for that distribution, but for its average value. So, it is useful to stipulate are both 0. The second one is often called a no slip condition. So, going back to this diffuser, so now we write the momentum equation in one direction, the x direction. So, x component momentum equation is equal to, we had that integral over Cs rho ds. So, how do you evaluate this integral? Just remember, you split into individual surfaces, right. Cs is split into 1, 2 and 3, and 3 anyway is 0. So, it comes down to 1 and 2. This u vector is replaced by component u, and u dot n will be minus u1 on the left plane and plus u2 on the right plane, and the areas are a1 and a2. So, this will be equal to rho minus u1 square a1 plus u2 square a2, and u1 a1 equal to u2 a2. So, this is equal to rho u1 a1 minus u1 plus u2. Which is u2 minus u1. This rho u1 a1 is, we will often use the symbol m dot, mass flow rate through the tube. So, u1 a1 is the volume flow rate and times density is the volume flow rate. So, since u1 a1 equal to u2 a2, for a2 greater than a1, u1 is greater than u2. So, this entire this term is negative. Okay, so, for the diffuser on the fluid medium, there is a net external force acting, which is negative and is given by m dot times u2 minus u1. Okay, so, what is the utility of this result? So, that we discuss as we go along. So, we have just obtained some preliminary answers based on our global form of the momentum equation. The opposite of a diffuser is a nozzle, in which exactly the opposite is going to happen and effects will be in the positive direction. So, complete that calculation. This is 1, this is 2. So, there is no change in the calculation, except that a1 is greater than a2, therefore, u2 is greater than u1, and f, the x component, will give you is equal to m dot times u2 minus a1, which is greater than 0. So, this result is not for the nozzle, it is not for the nozzle is that solid entity. The analysis is for the fluid medium contained, but that fluid medium there is a continuous flow taking place through it. For that control volume, you get a positive force acting on the fluid medium. So, I think you can almost expect that equal and opposite will act on the solid surface, which is sometimes called a propulsive thrust. Nozzle is often used to propel. Suppose you put some object, suppose you are sitting on the nozzle, you will be set into motion because of that unbalanced force, sometimes called the propulsive thrust. So, these are technical terms which you might have heard earlier, but now you are seeing it now in a formal setting. So, this is this term. So, in this case it is useful to have that force. In case of a diffuser, there is an unbalanced force. So, you need a separate structure to hold the diffuser in place. Okay. So, depending on the device being studied, the consequence of having either a zero force or a non-zero force would be distinct. In some cases it is parasitic, some cases it is useful. Okay, so let us go back to the flow in a tube geometry, where we found that the sum of all external forces acting on the fluid contained in the CV. So, I am just showing you the CV. So, you know it is the CV when I show these points A, B, C, D. And these points are on the surface. So, they are just shown so that you can break up the surface into parts 1, 2 and 3. So, sum of all external forces, we are talking about x direction. Let us say f x equal to turned out to be 0. So, how can we interpret or make use of this result? So, what are the insights we can bring in and to study f x equal to 0? So, here you recall that at the local level, this is a small fluid element and on the faces of that element we had introduced stress components sigma x x on the right face. So, there are similar components on all of them. Okay. So, I am not showing sigma y y, if you refer to the notes earlier. So, this is a compact notation for stresses acting on a fluid element. So, in the fluid medium, there is a distribution of forces. Through your global approach, we got the resultant straight away, but they arise from a distribution of forces. And on every phase, let us say AD, there will be normal stresses and shear stresses. Similarly, on CD, normal and shear stresses. Now, since we are talking about the x direction, the shear stresses acting on AD will be in the vertical direction. So, that sigma xx will be pointing to the left. Now, sigma xx under flow conditions is not necessarily P, but if you remember our discussion that if flow is mainly in one direction, in the other direction you can think of as hydrostatic. That will be a hydrostatic variation. Am I hearing the bell? Okay. So, that bell will stop the flow, so to say. So, we now look at forces acting on the control volume as a distribution whose resultant is capital F, is 0. Okay.